Hi, my name is Serrao.
And my name is Lili Piesanen, and we are rising high school seniors from New York City and New Jersey, working under Dr. Christine Simurda on the ICESat-2 team focusing on glaciers. We want to start off with a quick explanation of exactly what glaciers are. They're defined as an accumulation of snow and ice with sediment and rock that move down a sloped area due to gravity. A great description for glaciers is that they're like incredibly old and slow-moving frozen rivers. Glaciers vary in region, but most are in Antarctica, Greenland, or other cold areas, and they also vary in size, but overall they have been shrinking and melting at higher rates than usual due to global warming.
We started our research process by examining the available literature on glaciers. We learned about the intricacies and the glacier anatomy, which is shown on the screen, and we read many papers on remote sensing of glaciers, as well as the factors that affect the rate of melting. One of those biggest factors are crevasses, and those are the cracks inside of glaciers caused by stress on different ice layers. They vary in shape and size, and they're also more likely to occur on fast-moving glaciers. And an example of one is featured on the right hand side of the slide. On the screen I have like a few different types listed. For example, bergschrunds form at the beginning of glaciers where they pull away from the rock wall at the head of it, whereas radial crevasses occur at the corner of a glacier.
Our area of focus for this research project was Alaska. As you can see in the graph on the slide, Alaska has a large section with glacial cover, particularly along the southern coast. We chose this region because of the limited other research done about these glaciers, and we wanted to fill in the gaps within the scientific community. In particular, we concentrated on the Matanuska Glacier, which is surrounded by 3 mountain ranges and melts into a river at its base. It's approximately 27 miles long and 4 miles wide, so it's a huge area of ice to analyze. At the moment, it melts and deposits into the river at about 1 foot per year, which, although it doesn't sound like a lot, is much faster than the rate the glacier can form. Our hypothesis states that due to climate change, glaciers have been melting at an accelerated rate, and one of the visual indicators of the process of melting is crevasses. Therefore, we hypothesize that over time there would be an increase in crevasses in both numbers and in size.
We developed a multi-instrument approach to fuse different products in order to evaluate crevasse structure as well as their appearance. First of all, we have ICESat-2, which is made up of 6 different laser beams that detect individual photons. It's 10,000 hertz, so it shoots 10,000 photons down to the ground and receives them back. We also use Landsat 8.9 imaging, and we pan sharpen them, as well as 2 other Landsat products, the fractional snow-covered area and the NDSI spectral index. We also use the Aster products, the visible and DEM. We use the ATL08 in order to map data on the photon scale, and that helped us to precisely measure latitude, longitude, as well as elevation. On the right, we have some featured software and websites that we utilize. First of all, QGIS was used to insert different layers. We have the Jupyter Notebook, which was used to run Python scripts, and Open Altimetry, USGS Earth Explorer, as well as NASA Earth Data Search were all forms of gathering data, and we use Google Earth Pro to map our final results. On the screen, we have a listed data table, and these are the 4 major instruments we use. We just want to give a big comparison. List our spatial resolution, temporal resolution, the spectral resolution, and the type as well. So Landsat is a visible and thermal sensor. The Aster 9 is a surface radiance radiometer. Aster 14 is a DEM, as I mentioned earlier, and ICESat-2 is a LiDAR altimeter.
Our key data tool was ICESat-2, which stands for the second Ice, Cloud, and Elevation Satellite, which was launched in the fall of 2018 and is still active to this day. It has 6 laser beams, 3 weak and 3 strong, that come in pairs, that pulse thousands of photons to Earth's surface and measures which ones return and how long it took for them to return. It has a 500-kilometer altitude and a 91-day repeat orbit. And most importantly, it houses the Atlas instrument, which we used for this research project.
On the screen, we have our different ATL03 and ATL08, which are ICESat-2 data products. ATL03 is global geolocated photon data. ATL08 is land, water, vegetation, elevation. And on the right, we mapped these files processed into KML files in Google Earth Pro, and these are the ground tracks of the ICESat-2 satellite. On the screen, we have our specific visual data products. We have Landsat 8 and 9, the operational land image. We have the Aster modeling product, that's Aster 9. We have Google Earth Pro, as well as the NDSI, which is a spectral index for snow. Throughout our research process, there was a lot of data collection, but we also had to process all that data. So what we started with was finding the longitude and latitude of our location. That was listed earlier in the presentation. And we needed to process our visual files in order to reduce the graininess and increase the resolution. And we used the ICESat-2 products and we put them in for real in order to process our data. And those different results are listed on the right, and we use different files for different objectives. For example, the CSV files were used in the Python scripts and Jupyter notebooks, whereas the KML files were used in Google Earth Pro. We also had to go through and select the correct beam for optimal glacier overlap in order to choose which of the three listed were strong or best in our case.
These graphs on the slide demonstrate the change in elevation for certain time periods for the ground tracks from ICESat-2. As you can see, there are lots of peaks and valleys for each graph, which literally represent the physical crevasses and elevated portions. Although each band is taken from a slightly different portion of the glacier, these certain slices overlap, and in further research, we can analyze in depth the elevation changes of certain crevasses. Because the Matanuska is a northern facing glacier, as the x-axis gets larger and comes more north, the elevation decreases as the satellite approaches the terminus of the glacier.
This is just a continuation of Lili's previous slide. On the screen, we have elevation averages mapped over time per season.
On this slide is our final graph, which compares crevasse propagation for select bands over time. To create this, we used the Aster and Landsat 8-9 visible data to manually estimate the location and count of crevasses. The manual evaluation of the crevasses was compared with the visible data to those identifiable in the ICESat-2 tracks. As you can see on the graph, 3 out of the 4 subsets had an increase during the 5-year period. The most notable changes are in the winter 2020 band, which increased from 53 to 92 crevasses in the span of just 3 years, and the winter 2019 band, which increased from 30 to 43 over the course of 5 years. On the next slide, I will go more in depth on the visible data and crevasses for the winter 2019 band. This slide is just a highlight on the visual data for the winter 2019 band. As you can see on the slide, we have 5 years featured: 2005, 2016, 2017, 2019, and 2021. And this is just a visual representation of the data as well as a rough estimate of where the crevasses lie. Finally, we have the applications for our research. Overall, glacier research is vital to understand how entire regions and ecosystems react to our changing climate right now and predicting for the future. The examination of crevasses in particular serves to mark regional environmental changes such as temperature, wind, precipitation, and more, as well as the mark of glacier melting. The melting of glaciers have large environmental consequences, such as rising sea levels, change in habitats and biodiversity, as well as the loss of fresh water. And our research specifically provides analysis on a more remote and less studied glacier to the scientific community.
On this side, we have the sources. Lastly, we'd like to acknowledge all the people that have helped us here today. I'd like to start by thanking our mentor, Dr. Simurda. She's been super helpful over the past 4 weeks, whether that be through online lectures to working with her in person. We'd also like to thank Ms. Miller as well as Ms. Baggio for organizing this program, as well as the NASA's faculty, mentors, and chaperones for doing everything that supports us here today. Lastly, I'd also like to give a shout out to our ICESat-2 team for supporting us and all of our NASA's peers. As an aspiring scientist and researcher, NASA Seas has given me an opportunity to build upon my computational skills as well as collaborate alongside many talented peers.
Adding on to Chris, I found that working at Seas as a NASA intern has given me the confidence, expertise, and inspiration to continue following my goal in pursuing engineering and environmental science.